Good. Today I'm going to talk about StackMold. StackMold is actually a result of a master thesis of Tom Valkeneers, the first author. He is from the University of Hasselt, but he unfortunately couldn't make it because he's working in industry right now. This work is also done in collaboration with Dan Ashbrook and Ramakers. So let me tell you what StackMold is. With StackMold, we can build truly multi-material objects. For example, this functional multi-material headphone with embedded speakers. Let me start off with a simpler example, a multi-material turtle with embedded LEDs. So how does it work? We have this software tool that allows to annotate different material regions, and StackMold generates a laser cuttable mold. The user then embeds electronics and casts different materials in the mold according to the manual. Once done casting, the user removes the mold and reveals the multi-material turtle with embedded electronics. Right. So now let me motivate why we did this. So I will discuss 3 processes that are readily available that could be used for multi-material prototyping. First, let me start with CNC milling. CNC milling is traditionally done with a single material type. Making a truly multi-material object requires milling separate parts out of different materials that need to be assembled or glued. But this process of assembly and gluing takes a great deal of precision and can be highly challenging for novice makers. Then we have the additive manufacturing processes, like these industrial printers, like C-Corp or the Stratasys Connex. But these printers are limited in the materials that they can print depending on their print heads. Also, the cost of these printers and the prints are also very high, especially for novice makers. In contrast, we have this inexpensive multi-material FDM printers, but they are also often limited by dual extrusion or single extrusion machines. But single extrusion machines can have these add-ons like mosaic that combine multiple filaments into a single strand to print a multi-material object. Some research has also been done with rotating vats to realize multi-material as lay prints, but approaches like this are not yet mainstream. Last, we have the formative processes. Some research also has been done in optimizing the casting process like flex mold or metal mold, but none of these techniques actually support the creation of multi-material or multicolored objects. In industry, there is a multi-material injection molding technique that's called overmolding. This approach requires a new mold for every material present in the object and is very expensive. We took inspiration from these techniques and devised a new concept that we call Multistage Molding that allows makers to cast truly multi-material objects. With StackMold, we facilitate the casting of different materials and different colors by using a novel concept we refer to as multistage molds. These molds consist out of different compartments for casting different materials over time. So here you can see the manual instructing the user to remove temporary props and add layers, creating a new casting compartment. As you can see, the inner layers of the multi-stage mold exist out of individually laser-cut MDF pieces of wood. Optimizing the buildup of this mold and the casting steps is a complicated computational problem. To illustrate this, I will walk you through a simple example. Let's say we want to cast this figurine in 2 different colors. We cannot make this model into 2 casting because if we fill up the model with temporary props that you can see as dark gray and we cast only the blue part, the undercut of the neck prevents the removal of the mold. If you can read it, it's from layer 14 and above will not be removed. Therefore, the temporary props inserted in the left region can never be removed if the blue part is casted. So how do we solve this? We fill the green part with temporary props, but we leave the head out of it. So then we cast the other side with the blue material, and then we remove the temporary props. And then the mold, because we open the mold, we can move the temporary gray props out of there, and we create this new casting compartment. Then we build up the mold further, and we fill the blue part, the blue head with other parts of the props, enabling us to cast a new compartment with green material. After we remove the temporary props of the blue head, creating yet again another compartment for the last casting operations of the figurine. We now can fill this compartment with the blue material and the casting process is done. The only thing left to do is to remove all mold layers to reveal the figurine. Even for such a simple figurine, this is a very complex problem. Therefore, we built a software tool for optimizing the mold buildup that facilitates and streamlines the workflow. Let me now go into more detail on how this interface works. By applying the brush, we can define different material regions. Regions that are not annotated have the base material properties, in this example the blue material. Once sliced, the StackMold generates a multistage mold that is ready for laser cutting. So now let me tell you how this mold is built up. The mold consists out of laser cut layers and a box to facilitate their alignment. Layers can have temporary props that can be removed over time to realize the casting compartments. At every step, a bracket can be pressed into the slot, keeping layers together to avoid leakages. Every layer has break lines engraved into them to facilitate the removal of the mold layers after casting. StackMold also generates a custom manual that guides the placement of all laser cut parts and layers. These parts are marked with an ID using the laser cutter so that the user can easily assemble the mold. For smaller parts with no marking, or they're too small to mark, we use this paper with the corresponding shape and ID. For removing the mold, some layers come apart very easily, but others are destructively removed from the mold, facilitated by the break lines mentioned earlier. So, hopefully now we have a general idea of how multistage molding works. Now I will explain some additional features of StackMold. StackMold allows for seamlessly embedding electronics into casted objects. During the generation of the multistage mold, fixtures are added to hold the electrical component in place during the casting. Another feature of StackMold is that it can optimize the level of details in the casted object. Because of the sliced model layers, objects have staircase effects and therefore have less detail in different regions. To mitigate this problem, our software has 3 approaches. First, the user can specify the direction in which the details are rendered. Second, the user can control the mold layer thickness. Adjusting the mold layer thickness gives more detail and also increases the amount of layers. In future versions, we could also adopt an adaptive slicing technique. Last, we can define higher fidelity regions, and StackMold will generate 3D printed parts that can be inserted into the mold, and after casting, objects in these regions have much more detail. This last option leverages the insight that prototypes do not need the same level of precision in every region the object has presented in the Valkeneers system at Guide 2015. This technique significantly speeds up fabrication time as it only renders regions in high fidelity where it's needed. So now I want to talk a bit about the multi-stage mold optimization. StackMold optimizes the order in which all compartments are casted to minimize the number of casting and curing steps. Here you can see a representation of 4 layers from M1 to M4, and you can see 6 compartments, that's A1 to A4, and B2 and B3. A1 to A4 needs to be casted in the blue material, and B2 and B3 in the green material. So now we want to optimize the order in which these compartments are casted. To minimize the number of casting and curing steps, if we try to cast every layer individually, the casting order would be A1, then B2, then A2, B3, A3, and A4, like a zigzag pattern. In this approach, only layers A3 and A4 could be casted together, as well as all other blue casting regions, followed by a green casting steps. Therefore, in this case, we have 5 casting steps. So, if we want to cast it with lesser steps, the normal approach would be, let's cast A1 to A4 and then B2 and B3. But we end up with an invalid solution. Now, you will ask, why is this? Is For casting the blue compartment, we have props in the green casting compartments B2 and B3. If we cast A1 till A4, we're unable to remove B2. This is because M3 is blocked by layer A4 that's sticking out. So how do we solve this? First, a material volume can only be casted when all volumes below that are in direct contact are already casted. For example, A3 can be casted before B2, but B2 cannot be casted before A2 because it's not in direct contact. Because A1 is not casted yet, sorry. So in this model, these relations, we build up the volume dependency table. Here, for example, in this table, you can see that B3 is in direct contact with B2 and A2. When we now can build up a casting tree. When using this tree, all possibilities are considered. The most optimal solution that we thought of before is still in the tree, and is still invalid because we didn't consider the placement and removal of the temporary props. So to model the placement and removal of temporary props, StackMold verifies all viable sequences of the casting tree using an algorithm we described in detail in the paper. In short, this algorithm considers the following 4 relations between casting volumes. First, volumes in the same layer that are in direct contact, like A2 and B2 are connected together. Second, the second rule, volumes on top. It checks for volumes on top that are in direct contact, like B2 and B3 in this case. Then, as the third option, mold layers on top locks the volume material from B2. So B3 is on top of B2, so it cannot be casted. And then fourth, the material above, the material in volume above, locks the mold layer below. So these 4 parameters are considered in the algorithm. By considering all these relations, the following result is the most optimal and valid involving 3 casting steps. First, we need to cast A1, then A2, then A3. These are casted in blue. And then we can cast B2, B3 in green. And lastly, we can cast A4 in blue. So, for the last part of this presentation, I will give you some more details how we implemented some interesting features. First, StackMold has support for 2 types of annotating brushes. If we want the 3D volume selected, we use the endpoints to determine the region. If we only want to annotate a surface, we implemented an eroding selection technique. To use the eroding selection, the user can set the intrusion depth of the brush. What do we do if we have overhanging structures? If temporary props cannot be removed, we use temporary casts of beeswax to provide support. After all casting steps are completed, we heat up the model, allowing the beeswax to melt, and we can pour out the beeswax. So here you can see that we cast temporary beeswax. After this is hard, we disassemble the mold and we reassemble it to make a casting volume for the plaster. Once we casted the plaster and it's fully hardened, we can heat up the model in an oven, therefore melting the beeswax and just pour it out as a support structure. So now the vase is fully hollow in between. So I'm going to skip that one. So let me briefly talk about limitations and the future work of StackMold. Although we use some heuristics for pruning the solution space sometimes can be large for complex problems. What are the solutions for that? We can use more heuristics for pruning the casting tree, for example, processing materials volumes with the same material properties first, or prioritizing material volumes that are connected across mold layers. As a third option, what we can do is optimize groups of layers individually. When it takes too long or it's too expensive to calculate the most optimal solution, we optimize for groups, as you can see in the image on your right. This approach is significantly faster as it optimizes the buildup of groups of layers and thus approximates the optimal solution in which the buildup of all layers is optimized. And lastly, what we could do is use some meta heuristics to optimize the pruning of the casting tree. So for some objects, an optimal solution is still impractical. For example, this checkerboard, we cannot optimize more for this or this Christmas tree. It's going to be a lot of steps, and it's going to be labor intensive because you have to cast all separate layers in a different color. We have also some material limitations. First, some casting materials are incompatible. Some components in one casting material can have influence on other previously casted materials, deteriorating it. And secondly, some materials are hard to adhere to each other. So an interesting way to solve this is using mechanical hooks. So to sum up, in this paper, we contribute the concept of multistage molds. Molds consist of multiple casting compartments over time that allow for casting multi-material objects. One of the most interesting qualities of this project is embedding of existing components, objects, and electronics that are very convenient. With alternative fabrication techniques such as 3D printers, this is oftentimes much more cumbersome. With this, I would like to open the floor for questions.
Stephanie Müller from MIT CSL. Hey, I'm here. Great talk. I really loved the new fabrication technique. So you talked a lot about like the geometry and how to cast everything, but can you also talk more about which types of materials we can now maybe cast together that enable some new interactive device applications? So these are mainly like different colors, right? Which you could also do with 3D printing, but what's maybe some materials that cannot be 3D printed, but now you have this new multi-material fabrication process?
Thank you. What's interesting is these examples are silicon-based, as you said, but they're different shore hardnesses, so that's the first thing where you can experiment with. But then, if you will want to go further, you could go and do some acrylic casting that's very hard to 3D print, or just embed wood parts of some carbon fiber, or everything that can go into a mold, and you can cast something that's liquid on top. Could be used in this mold. For example, in the headphone, there's a metal structure inside of it just to test if it's springy enough. So you could use different materials, all materials that are castable you can use, but also existing materials. And I think that's very exciting, like cast a hinge inside of an object, what's more difficult with 3D printing, I think. Or I don't know, electronics in different layers on top of each other. You can just have different compartments where you can route the cables in between, and you don't have to wait for the printer to reach a state where you can put it in there.
Awesome, thank you. So to keep us on time, we're going to go to the next presentation, but if you do have more questions for Danny, you can find him at the end.